Hello and welcome. This is section 3 of chapter 15 and entitled Energy in Simple Harmonic Motion. It's a short section, but there's some comments and some interesting things that we should try and glean for later topics down the road. And so as a quick review, we just consider a mass attached to a spring on a vertical wall, on a frictionless surface, all these idealizations, and we look at the energy diagram. It is certainly a potential energy that's a concave down parabola. When the total energy is constant, right, it's the total energy graph is a straight line, horizontal line, then the kinetic energy is total energy minus potential, which in this case is just a down parabola, concave. The potential energy is concave up, excuse me, right? And so this system, much like any system that oscillates, certainly satisfies the conservation of energy equation, which for the mass on a spring is simply 1/2 mv squared plus 1/2 kx squared, where again, x is a coordinate that indicates the displacement from the equilibrium point, which has been denoted as the origin, is derivative of that displacement. Even though this is, chapter 15, it's still helpful to review those basic chapter 2 concepts. So the energy is certainly constant, and we also have an expression for the energy of this mass at x equals a plus or minus a for the amplitude of the oscillator. It's equal to only potential energy, which is just half, which is actually just Ka squared. And then the energy at the center, is actually K is equal to K. At x equals 0, it's just equal to K. And so the magnitude of the energy at there is equal to 1/2 m times V max squared. And so these are easy enough expressions to pick up on for the potential and kinetic energies of the oscillator. And once again, we see this figure in this graph down here, what it looks like. Well, what would it look like in time? This is what's kind of interesting, is that both of these energies act as squares of the position versus time. Remember, position versus time for a simple harmonic oscillator is expressed as the amplitude times cosine of the angular frequency times t plus the phase constant. And so these graphs are like cosines and sines squared. So the energy is always dipping between plus and minus. It's always positive, rather, but it's always switching between these squared trigonometric terms. Right? And then sure enough, we see the value in a period t, the energy goes back to its initial value, time equal to the period t. So this is stuff that we introduced in chapter 10 about the potential energy, and it might seem like it's not that new, and because it's not. Certainly the energy as a function of time is different, and it's helpful. The real comment I want to make about this that I think is transferable to later topics in physics is this idea of frequency. If you look at these equations, the energy, right, if you look at these equations, obviously the kinetic energy is equal to, the max kinetic energy is equal to 1/2 Ka squared. And so that means that the maximum speed, if you do the typical canceling these 1/2s and dividing by n and taking the square root, you find that the max speed is equal to it's proportional to the frequency. So down here, you can find that when we define the frequency, we get that the frequency of the oscillator is proportional to the square root of K over m times that factor of 1/2 pi. And we have these three variables, omega for the angular frequency, f for it's not linear frequency, but it's just the actual frequency in hertz of how many times per second for a complete oscillation, where omega is the rate at which angle in the phase diagram is being swept out, t is the period. Again, they're all the same information, just expressed different ways. And we see that the energy of a system is really proportional to its frequency, whether we're talking about angular frequency or linear frequency. Those are just, they have exactly the same information of them. They're just related by a factor of 2 pi. And so this really gets into other systems, because for this simple mass on a spring, it obviously shows that the frequency depends on the stiffness of the spring and also the mass of the object. Typically, in realistic physical systems, the mass is usually constant, and something like the spring constant changes. An example of this is molecules, vibrations in molecules. So if you consider a simple oxygen molecule, like a diatomic oxygen gas molecule, O2, right? There's 2 oxygen molecules that are connected by this molecular bond. That molecular bond behaves to some extent like a spring, and the energy, the vibrational energy of that oxygen molecule then is just proportional to how rapid that bond is vibrating. So it's like 2 masses connected by a spring, and so they're going to oscillate back and forth with each other. Now, the masses of those certainly don't change, right? There's just oxygen atoms. But you can in a sense change the spring constant of this system by giving it more and more energy. And how do we give molecules energy? Well, we shine light on them. And when we shine light on them, that changes the dynamics. That increases the temperature of it, which in a sense increases the effective spring constant, increases the angular frequency. So that's an example where in molecular dynamics, the energy of an oxygen molecule or an energy of a molecule depends on its frequency. Another instance is light itself. Light can be modeled as these little packets of energy called photons. And the further down you get in the so-called electromagnetic spectrum, the more energy those packets of light have, and their frequency is also larger. Blue light is wiggling a lot more rapidly than red light is because it has more energy. And there's many more examples like this in science and engineering, where the frequency affects the total energy of the system. It's helpful now to go back and consider like acceleration and the motion diagram of them. It's certainly, the acceleration is always changing and it's always pointed towards the center. And so the motion diagram is going to look quite, unique. And so when we finish that, this is more a conversation that is, well, it's kind of more left for the dynamics of simple harmonic motion, but the result is that the acceleration is proportional to the displacement. And I'll expand upon that more in section 4. But for now, thanks for watching. We'll see you at the next video.